Can we start? Okay. So good afternoon, everybody. My name is Giuseppe Santoro. Okay. Let me start with a brief introduction. I work at SISSA, a PhD school, okay, which in fact is something you should possibly consider if you want to continue with the graduate studies. It is a possible place where to do a PhD here nearby. In fact, we have a program for, there are special fellowships devoted to diploma students. Okay. Should we close the door? Maybe we close the door. Okay. We will do quantum mechanics together. If you need to contact me, I suggest using the email as the fastest way to reach me. Alternatively, there is a telephone number which you can use to reach me, okay? But this is the best way because I'm not sure I will always be there. Okay, so I ask you to sign a sheet with your email so that I can communicate with you if I ever need through email, just in case there is something, or to distribute lecture notes also in a PDF form. I have basically written very sketchy notes, which are basically what we will say in class, okay? Not many pages, very, very sketchy, but it's a guide that you could use together with the recording of the lecture. What else? Yes, a couple of recommendations. One is about books. There is a tendency, I remember even myself when I was a student, to try to read many books as if, you learn more if you read from many books, which is not always the case. In fact, it's often counterproductive. Because every book uses a slightly different notation, and therefore you tend to get confused by reading from many books. The best thing you can do is to pick up a single book, reasonably authoritative, okay? For instance, a book you have already used, or some other book which is well established, not just private notes by some professor like me, but some book, some internationally known book, and you stick to it, okay? Essentially, everything we will do is there with a certain specific notation, and you try to work it out, okay? The best you can do is to actually do the calculation yourself with your own notation, with our own notation, okay? So that you really get very, very confident with the algebra behind a certain subject and so on, okay? So reading of the type that you do when you read a novel, okay? It's not useful at all, okay? So don't do it at evening before you go to sleep, because that's not the type of reading that you need. You need to sit on a table, okay? Have your book, your notes, and a piece of paper with you, and while you read, take notes, do the algebra, redo in a different way, really work on a page in a substantial manner, okay? Not just go through it and then you close the book and you go somewhere. That is useless, okay? And the more so if you just read from many books, well, it's just a very confused image that you get of the subject. For a while you seem to understand things, but after a while you will completely lose contact, okay? So I discourage this type of attitude. Just do very slowly your homeworks, for instance. Homeworks are very important. That is the second message I want to give you, because they give you the opportunity to really test your abilities, okay, your problem-solving abilities, what you have understood, what is the difficulty that you have. Write them, okay? So always write the homeworks and give them to me. I insist you give them to me not because I will read every single sentence you write and check and give marks, okay? That is not the idea behind the homework. The idea is that you confront yourself with a certain difficulty. If you can solve it, there's no need even to mention to me. You just write it for yourself mostly. If you cannot solve it, there is the nice thing, okay? Because it means that you have a difficulty which should be solved, okay? So your duty is to try to do the homework and point out to me the difficulty, okay? So that is the precise moment when we should talk together, we should see the exercise together in class or after class, whatever, okay? So do not try to hide the difficulty, okay? But on the contrary, just point it out. Again, it's not to give you marks, okay? So if you have a difficulty, you will get a lower mark. Not so. In fact, if I see people participating, showing their problems, having discussions, that is better for you, okay? Okay, having said that, books, just a quick mention. I would suggest you a not too complicated book. For instance, a book like Landau, Lifshitz, I think it's too complicated. For me too, sometimes. I personally find reasonably good this book by Gaziorovitz. This is an old edition. There is now a third edition or so. This is a intermediate low level, not very, very complicated. There are other books which you could consider, especially for certain parts. One very nice book is by Sakurai, Modern Quantum Mechanics. I warn you, not Advanced Quantum Mechanics, which is too complicated, but Modern Quantum Mechanics. Another excellent book is the book by Cohen, Tanuji. This is, however, very, very thick, okay? It's 2 volumes like this, okay? So it's quite the opposite of sketchy notes that I will give you. I mean, it's very, very detailed. Everything is done in full length. And it might be a good source for certain parts, okay? So, for instance, you want to understand in full glory and in full detail a certain exercise which is done there, then you might go and read it. But as a book to use overall the course, I warn you, it's very thick, okay? So be prepared to read a lot if you really want to use that. But the level, it's, I mean, things are explained in all detail, okay? So there is no mystery like in Landau. It's quite the opposite of Landau. Lots of words, lots of calculations, okay? So this, I would say, are the 2 possible other books. This is probably more advanced, so maybe this is a lengthy source of material, okay? Gaziorovitz is definitely a level that is probably more the right one, okay? You have questions about books. You have, for instance, a book that you yourself use that you would like to check. You can ask, or you can ask after the lecture. Okay, so don't feel afraid. If you have your book and you want to check with me if it is a reasonable one, we can check together. Okay? English, if I'm speaking too fast or you do not understand something, don't be afraid, just interrupt me, okay? The first thing is to communicate, okay? So if you don't understand what I say for some reason, the lecture obviously communicates less. Okay. So let me start now. Thanks. Let me start with, as a kind of introduction to quantum mechanics. By the way, the course is called Advanced Quantum Mechanics, but there is very little advanced, okay? The only thing that I assume is that you have seen some quantum mechanics before, okay? For the rest, I will really do things essentially from the beginning, okay? So I give for granted that you have seen quantum mechanics, so you are not totally foreigners to this concept, but we will be very basic, in fact. So as a kind of introduction to this thing, let me show you a few things, okay, which are taken, in fact, from a seminar I was giving to some students of a communication course. They will be in Italian. You will see something written in Italian, but don't worry. I mean, it's just as an excuse for me to show you a few things. This is also a nice demonstration of why quantum mechanics, well, I shouldn't say became important again recently. I mean, quantum mechanics has been important since its discovery, but more so lately. There have been a lot of discussion and a lot of research concerning quantum computing. Probably you have heard something about this. I mean, the computers we have here are digital computers based on standard, by now, electronics, which is essentially classical physics, okay? They are based on transistors, 1 and zeros, but they work essentially classically. There has been a very nice suggestion more than 20 years ago by Feynman that instead of working with 1 and zeros classically, you might work with 1 and zeros quantum mechanically and devise a machine that computes things quantum mechanically, which in principle should be much more powerful than this object in front of you. Okay? So this is what is called quantum computing. It is just an excuse to refresh for you the basic things of quantum mechanics in a very short presentation. Then we go again, lights on, and we discuss on the board the basic things. Okay? So I would say here, let us first get the screen. Okay, the light. Okay, can you? Okay, so this slide is called the digital computer, and is essentially a tribute to the inventor of the computer. Is this man here? Oops, I'm sorry. Okay. It's called Bardeen, okay? He is the same person of the theory of superconductivity. Bardeen, Cooper, and Schrieffer is the B of the BCS theory of superconductivity. He was a very, very bright physicist, and he discovered the transistors together with a couple of other people, and also made this very important contribution to superconductivity. This was in Bell Labs in the US in 1947. It is essentially a device, an electronic device that can have two states of current passing, current not passing, controlled by some voltages, okay? And the device itself lends itself very, very nicely to being a 0 and a 1, okay? The current passes 1, the current doesn't pass 0, okay? Therefore, is a very nice tool to play with binary information with binary numbers. So binary numbers can be then summed and multiplied. You can do operations on this thing if you have many, many of those transistors. At the beginning, they were bulky things, okay? The object there, I think, is the first one. It's a sizable object. Now, with the process of miniaturization, you can really make quite a lot of them inside a small chip, okay? There are millions of those transistors integrated together in a small chip, okay? Now, obviously, there is a limit to miniaturization. How many can you pack in a small chip? Essentially, there is a lower limit. You cannot really go beyond a certain, I mean, to make a single transistor, you need a few, not certainly one atom, okay? You need more. But Feynman, who was a very, very great physicist, thought of maybe the true limit is if you can make 1 and zeros on a single atom, okay? So in some sense, this is the ultimate limit. You cannot go below in miniaturization if each atom is itself a source of 1 and 0, right? Okay? Because otherwise you should go to, I mean, physics that is not condensed matter. It is nuclear physics, which is certainly not easy to control in everyday life. Okay? So this is the ultimate limit. This is what he proposed in 85, and I would like to read from the abstract. He says, but we are going to be even more ridiculous later and consider bits written on one atom instead of the present 10 to the 11 atoms. Okay? Such nonsense is very entertaining to professors like me. Okay? It shows you also how physicists produce new ideas. They just play around with concepts which are sometimes even ridiculous at first, but then people start working on them, and in the end, things that looked ridiculous when they were first proposed, they appear to be very, very nice ideas. Okay? So what is the idea? Well, let me just, before I present you the idea, step back a little bit, okay? So you probably know very well that in the beginning of the 18th century, there were experiments on light, which definitely proved that light was made of waves, okay? There was a famous experiment due to Young, okay, where he essentially got some light from a slit, okay, narrow slit, that then impinges on two narrow slits here, okay? So this one is just to make from a very broad beam to make a narrow source of light, okay? This narrow source of light then goes into these two slits, okay? And you see here the two slits giving out some light that when observed on a screen, for instance on a photographic screen or on a screen that is sensible to the light that goes there, shows this very, very surprising pattern, okay? So contrary to what you would expect if these were balls passing through the slits, okay, then you would have just a spot here in front of the first and a spot in front of the second. On the contrary, you have interference fringes, okay? So you have the maximum of visibility in the middle, and then you have dark spots, and then again visible spots, and then again dark, and so on, okay? This is what typically waves do when they interfere. If you have, say, waves coming out of two, for instance, two cliffs, which have a small slit in it, okay, the two waves then interfere past the cliffs, and they superimpose, they have destructive and constructive interference, and that's pretty much what you expect if you have waves. Okay? So, yeah, here is a cartoon, essentially. You have a wave, okay? It goes through the two slits, and then there is a wave coming from the first slit, the wave coming from the second. They start interfering. You should think of a pond with two circular waves created. They interfere, and they form an interference fringe, okay? But what about light, okay? Are they, I mean, really waves, or are they particles? Well, this experiment seems to definitely answer the question. It's just wave. Nevertheless, even the things that look more clear, they are not always infinitely clear. And nowadays, you can repeat this experiment by just having very, very faint sources, okay? So you can really see not just big beams of light, but send, by now we know, the photons essentially one by one, okay? So really you see the photons accumulating on the screen. They come, tunk, 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 one by one, okay? Nevertheless, if you wait and you let a lot of them to go through the double slit, they still form the pattern, okay, that a wave would form, okay? So in some sense, you can now see a duality of this light. The light forms interference pattern, but is also made by individual things touching on the screen, okay? So this is already something new with respect to Young's idea. And what about electrons? Quite the same. You can repeat a similar experiment with electrons. I don't know if this is visible now. Here, there is a screen where 8 electrons only are registered. You see, 1, 2, 3, 4, okay? Here, there are 270 electrons. They still look rather uniform, just randomly scattered. And here, there are 2,000 electrons. You start seeing that they are not really uniform. And when you have 6,000 electrons, you quite clearly see that they are not uniform at all, okay? So electrons are individual particles, but the way they pass this experiment, this double slit, reveals that each electron interferes with itself in some sense, okay? And you see very clearly the bright and dark spots on the screen, okay? So electrons behave in some sense like light. And this is a cartoon, okay? If you have some machine gun and some bullets, okay, and the bullets pass through 2 slits, obviously they can either pass from one slit and create, therefore, a bump of bullets hitting this place, or they can pass through the second slit and get the bullets there, and therefore on the screen you expect 2 bumps, one in front of the first and one in front of the second slit. Okay, so these are classical projectiles, what they would do. Okay, if you have waves, then you send waves to the thing, and as I discussed before, the 2 waves interfering form a fringe. If you have electrons or photons, okay, they kind of do in some sense both. They behave like particles, but these particles are very special. They are particle waves in some sense, okay? And so they really interfere, even down to the level where you can individually count them, okay? So if the question is, are the electrons particles or waves? The answer, the official answer, at least till today, is they are both, okay? When you reveal an electron on a screen, you reveal it as a certain position x, exactly like a particle would do. Nevertheless, there is a certain probability of finding this in x, and this probability of finding the electron at a certain position x on the screen is the square modulus of the so-called wave function of the electron, okay, which is a wave, okay? So it's a complex object, which is the subject of our course, okay? So this is a smooth introduction to what we are going to see in a very short while, okay? So psi of x behaves like a wave, okay? And obeys an equation, which is the key equation you will study is the Schrödinger equation, okay? The modulo square of it represents the probability of finding the particle on the screen at a certain position, okay? So it is at the heart of quantum mechanics that the state of a system at a certain time t is represented by a superposition of, you see, this is the state of a particle at a certain position on the screen, okay? Neither of them is the ultimate state. It's a superposition of them that matters, okay? With an amplitude that is just the wave function, okay? So the overall state of the system is not a single classical like point x, but a superposition of all of them with the wave function as amplitude of the superposition, okay? And P is the probability, the square modulus of psi, and this psi obeys this very, very important equation, okay? So it depends on time and on position. It's first order in time, while it generally has second order derivatives. This is the so-called Laplacian. It's essentially second derivatives, okay? This is the classical potential, okay? And this is h bar, okay? A quantity that we will soon meet. And this is the mass of the particle that you are considering, okay? So this is called the Schrödinger equation. It was invented by this man here in the 20s. Okay, just before we quit this small presentation, another thing which has to do, in some sense, with classical physics. You probably know that drums are the simplest, probably, representation of waves, okay? A drum is a membrane, okay, which is held fixed on, for instance, a circle. Okay, usually they are circular, okay? So the membrane is just sticking on some board on a circle, but then can fluctuate inside. And it can fluctuate in very, very many ways, okay? So by hitting it in appropriate waves, you can get a lot of possible vibration of this membrane, okay? By the way, this is still Feynman, who was also very fond of playing drums, okay? So for some reason there is... okay, here I draw some of the waves, depending on the nodes that the oscillation forms, okay? The oscillation, well, maybe it's better if I use, okay? So you see, this is a wave that is fixed on the board and a change of sign in the middle. This is probably one of the simplest waves that you can form. There is always a place where the oscillation is zero. You see some place, so it can be positive, negative, but there is a place where it is zero. So this is a zero of the function, okay, inside the overall zero, which is just the exterior, okay? So this is n equal 1 in the sense that there is one extra zero inside. But you can form other waves. For instance, this wave, okay? You see here there is a line also where the wave is not, is zero, okay? Here, okay? So there is some more complicated pattern, and there are even more complicated patterns, okay? You see how many strange zeros that not necessarily have cylindrical symmetry, okay? So lots of solutions you can get to the wave equation on a very simple geometry like a circle. All of them have a certain frequency, okay, which is usually different from one to the other, okay? And this makes a different pitch, obviously, for the sound that the drum makes. Okay, so this is classical physics, but surprisingly, quantum mechanics also has some features that are just exactly the same. Now, this is the schematics. In fact, is an electron microscope figure showing the surface of, if I remember well, is copper. And the bumps that you see here are iron atoms. Okay? This was made at IBM in the 80s, I think, just after the invention of the STM. I don't know if you have heard of this magical instrument. It's called scanning tunneling microscope. It's essentially a small tip, okay, ending essentially with a single atom, which you can scan very close to a surface, and by applying a voltage, you can make a current pass through the tip and the metal underneath, okay? And depending on how big is the current, you can essentially gauge how high the tip is on the surface. So you can make out the topography of a surface by scanning this small tip on top of it, okay? And not only that, you can even use it to move atoms. You just essentially almost touch an atom, and then you move it along with the tip. And that is what they were doing here. So you see at the beginning, the irons are a little bit scrambled around, just the beginning here of a construction of this fence that in the end becomes a very nice circular, they called it corral, okay? Because it's essentially a round fence. And inside, look what is there, like a pond. You see the wave inside? The wave is the electron themselves. In the surface of copper, there are electrons. The electrons see the fence, okay? And they see the fence exactly like waves would do, okay? So they oscillate in a way that is compatible with the fact that the fence is a fence, okay? So the wave has to have a certain zero somewhere, exactly like a drum would do, okay? So electrons behave like waves. By the way, you can see the density of electrons because of the tip, okay? The tip can also register density of electrons. And so it's a sensible way of measuring a wave. And here is the photograph of the wave. You see, there are quite a few oscillations, not just one like there, but that's a wave, like a wave in a drum, okay? And this is a photograph just from the same thing, but just seen, well, from the side. Okay, you see the irons and the wave of the electrons inside. Okay, so this is more fancy. The corral now is not a circular fence, but is kind of a stadion. Okay, so two semicircle connected by a straight piece. Okay, and obviously the wave inside is more complicated than just this simple-looking circular. They can make, you see, all kinds. They played a lot with these things, obviously. Okay, it was quite fashionable to have this called quantum corrals. Okay, to visualize the waves that you can form. Waves due to the electrons again. Even more, towards the end of the course, we will discover another very important thing, which is the spin. It was discovered experimentally by this guy here called Stern, and theoretically by a very important physicist of the past century, Dirac. Okay? The spin is an intrinsic property of an electron, or other particles also, is a kind of intrinsic angular momentum. Okay? It's as if the electron was spinning, okay, on itself and being charged, generating a magnetic moment. But it's really not the orbiting of the electron itself. It's an intrinsic property, okay, of relativistic origin, and the spin of the electron can be in two possible values, so 1 plus 1/2 or minus 1/2, so like a magnet that can stay up or down. And obviously this is a very nice way of having 1 and 0. You just say that if the spin is up, then you call it 1. If the spin is down, you call it 0. So another digital element. But the nice thing about this digital element is that due to the rules of quantum mechanics, you can make superposition. Okay, remember the psi of x, the state is a superposition of the possibility of being in any place x. Okay, and here again, the state is a superposition of being up and being down with two, in general, complex numbers. So this is like the wave function we had before. Okay, just for two values. And with that, obviously, well, first of all the nature around us is due to this very simple property, okay? The periodic table of elements and the way elements are organized in atomic shells and so on, as discovered experimentally by Mendeleev, and with the crucial understanding due to Pauli, the Pauli exclusion principle, that forbids electron from saying with the same spin in the same orbital, okay? So it forces to occupy the orbital with opposite spin, and this explains the filling of the different atomic orbitals, okay? So nature is a result of spin, although it's not obvious if you just look at the table, but the table is highly quantum mechanically in its very deep nature. And not only that, obviously, for our quantum computation story, the nice thing about having superposition is that now you, instead of working with a transistor that can be either 1 or 0, now, in principle, you have a system that can be in a superposition of 1 and 0s, which is a little bit more. In some sense, classically, either you have alpha equal 1 and beta 0, or vice versa, alpha 0 and beta 1. A transistor can be either on or off, nothing else, okay? A spin can be more. You have, in fact, an infinite variety of alpha and beta, okay? These are complex numbers. The only requirement is that the alpha square plus beta square is 1, but there's still a huge freedom, okay, in having states of the system that are not just 1 or 0, okay? And this very large freedom is at the basis of the idea of doing quantum computations, okay? Just before leaving you with this, bear with me for 2 more minutes. Obviously, if you try to apply this idea of superposition of states to the classical world around us, it gets into paradoxes. Very easily you can get into paradox, and the most famous one is the famous paradox of the Schrödinger's cat. You've probably heard of it. It is the following paradox. There is an intrinsically quantum mechanical thing, like some nuclear reaction that can emit some very high energy photon, some gamma ray, okay? Nuclear reactions typically emit this kind of things. This is the reason why they are dangerous, okay? Because they emit high energy photons, okay? They happen to be just processes that occur every now and then. So you might say, okay, either occurs or not occurs is my 1 or 0. And obviously that word is highly quantum mechanical. So the system has emitted or not emitted this photon. But then you can build a classical machine around. So if the photon was emitted, you trigger a hammer, okay? And the hammer breaks a glass where there was some poison, okay? And the poison kills the cat, okay? So if the photon was emitted, say, state 1, the cat gets the poison and is dead. If, however, the photon was not emitted, state 0, then obviously the poison is in the glass and the cat is alive, okay? Obviously, whenever you have 1, so the photon is there, the cat should be dead. Where you have 0, the cat should be alive. So if you carry on this superposition, you would seem to imagine that the state of the system, okay, this box here, is really photon 1 and dead cat, plus, this is alpha, plus beta, photon 0, so no photon, and cat alive, okay? But obviously, I mean, the cat cannot be just in a superposition like a photon would be. Okay, the cat is not a quantum mechanical object, it's a macroscopic object, and obviously this opens lots of questions, even philosophical, of what is the level at which quantum mechanics really becomes classical physics, and how you reach a classical physics intuition and understanding out of the quantum mechanical basic laws, which are still true when you have many, many things interacting. We'll not touch these very difficult things. Just to warn you that obviously if you have not a small object which is very well controlled and quantum mechanical, but you have a very large object, you should not use just without knowing the rule of quantum mechanics, because obviously it's a very complicated system that needs to be studied more. Okay? So, just to finish with the computer, you see that people have really realized with the spin of very, well, say complex molecules, but not so complex. In fact, this molecule has 5 spins in it, okay? This fluorine here, okay, has a spin. And obviously with this molecule and 5 spins, you can think of having 5 bits, okay? But these are quantum bits because they are not just 1, 0, they are alpha 1 plus a beta 0, okay? So they are quantum bits, and with 5 quantum bits, you can do already a lot more than with 5 classical bits. Obviously, the real dream is to extend it to having a real computer with quite many bits, okay? But in principle, this is the first step towards realizing what Feynman had in mind, that bits 1 and 0s are written really on a single atom. This would be the spin in this case, okay? So, well, this is just photographs of the important people that during last century have contributed to this field. So this is Schrödinger, this is Bardeen, Dirac, Feynman, Pauli. This is, by the way, Oppenheimer and von Neumann. Von Neumann was one of the founding fathers of quantum mechanics. He was a mathematician, but he was also the father of the first big digital computer, ENIAC or MANIAC. I mean, they were doing it in the US, okay? Okay, so I would say that this is the end of our small presentations. If you have questions, this was just to entertaining you 10 minutes. Okay, so if you have questions, otherwise we move to the actual lecture. Okay, so I will start with some very basic introduction. The quantum mechanics books usually have their first chapter, which is introductory, okay? So they'll talk about what I'm going to say in 10 minutes in quite a few pages, okay? So I invite you to do this reading, quite careful, okay, but the reading, okay, in any of your favorite books, okay? I will be very, very sketchy on that, in some sense assuming that you have also seen these things in some past, okay? So the history of quantum mechanics, I would say, starts at the beginning of, right after 1900, okay? And the first 30 years of that century, so from 1900 to 1930, they are really the years that shook physics most, probably. And in fact, there is a very nice book this is just a novel type of book. This is written by Gamow, a very famous nuclear physicist, and it's called The 30 Years That Shook Physics, okay? So it discusses many of these brilliant physicists that are the fathers of our current understanding of quantum mechanics, relativity, and so on and so forth, okay? So very, very profound revolutions in the physics as it was known in the century before. Classical physics, classical mechanics, electromagnetism even, okay? They were very, very studied and understood, but relativity and quantum mechanics changed a lot our understanding of many, many things, okay? The story has to do with both understanding of light experiment and of electron in the matter, okay? I must warn you, you must put things in perspective. Electrons were not known in the, 2 centuries ago, in the 1900s, okay? They were discovered at the end of the 1900s, 1897 or something, okay? So in some sense, it's obvious that before you discover electrons, you cannot really do any quantum mechanics, because quantum mechanics is seen at play when the mass of the particles that are playing a role is very, very small, okay? Until you have a chair, you would never understand that classical physics was not good, okay? Well, obviously, if the chair is accelerated to a velocity that is very, very high, then you would discover that you have to invent relativity to describe it. But to discover quantum mechanics, the chair would not be good at all, because the mass is too big, okay? Whatever the velocity is, okay? And light particles, like electrons, are the right theater where to understand that things behave non-classically, even at the opposite regime, okay? So classical physics fails in 2 ways. One is at very high speeds, okay? And this is the kind of failure that Einstein understood, the beginning of the century, okay? Special theory of relativity. The other opposite failure of classical physics is masses and length that are, atomic size, okay? There again, there is a failure of the classical laws of physics, but this is quantum mechanics, not relativity, that describes it. In fact, we will discuss for the rest of the course about mostly electrons, but the story really starts with electromagnetic radiation, so with what we now call photons. Essentially because one of the paradoxes that the people at the beginning of that century had to confront themselves was the distribution of electromagnetic radiation in what was called a black body, okay? So essentially an oven, a furnace, okay? You probably have seen always a furnace, I don't know if you, where you just cook the bread, okay? You can see the bricks, okay, on the surface of the thing if you peep inside, and depending on how much you have eaten the oven, you will see the color of the bricks changes, okay? They start being just pale and reddish, okay? And the more you heat it, the more they become more towards the white, and, okay? The color of the bricks is associated to photons emitted by the atoms of the bricks, okay? Which are obviously very, very highly excited, and they emit photons, and they reabsorb it also, okay? So there is a process of absorption, emission of photons by the atoms in the brick, okay? And what is inside, therefore, is electromagnetic radiation, okay? So you cook your bread with electromagnetic radiation, nothing but that. the distribution inside, if you are at equilibrium at a given temperature, so you don't keep heating, but you maintain your temperature, say, fixed, 300 degrees, 400 degrees, fixed there. The distribution of energy is fixed, okay, stable, and people knew how to measure it in different frequency range. There is obviously radiation of all frequencies inside, okay, all spectrum. So from red to blue and whatever, even higher, okay? So all kind of electromagnetic frequencies are present in the oven. Obviously, depending on the temperature, this distribution is more shifted towards the red or towards the blue, okay? So the place where the maximum of the energy is centered in the spectral region where it is, it depends on temperature, but people knew how to measure it, okay? Unfortunately, didn't know how to calculate it. Although, in principle, the equations, Maxwell's equation for the wave, for the electromagnetic radiation were pretty well known. Thermodynamics was well developed, so you might think of applying the rule of thermal equilibrium to the waves of the electromagnetic field and calculate the average energy at a given temperature, as you would do for any other classical thermodynamical system. But it didn't work, okay? In particular, if you plot, what it was known is that if you plot the energy density, okay, as a function of the wavelength of the light that you look at, okay, and you divide by the temperature to the 5th power, and instead of measuring simply as a function of lambda, you measure as a function of lambda times t. Okay, so you put on the x-axis the wavelength of the radiation times the temperature of your black body. Then there was essentially all data that you could collect at different temperatures. They were all staying in a single curve. Okay, the single curve had a tail like 1 over lambda to the 5th. Okay, for very large lambdas. This, people knew how to calculate. Classical physics would give you this, okay? So this is classical physics. However, as you go down to lower wavelengths, which you know the wavelength is higher frequencies, okay? You know that there is a relationship. So lambda is equal to c times the period of the wave, which is the inverse of the frequency. Okay? C is the velocity of light. So as you go to lower lambda, which means higher frequency of the electromagnetic radiation, this curve, instead of proceeding like that, curves down and does like that. Okay? So this thing was not given by classical physics. Okay? So people tried very hard, but this always escaped. And it was Planck that understood how to really make sense of this whole thing. And he understood that the crucial thing that you have to assume is that the energy of a wave, inside the oven there are waves, the electromagnetic wave, is not arbitrary. You cannot have an arbitrary energy. If you have a wave of a certain frequency, nu, then the energy that that single frequency can have is proportional to nu, and you can have multiples of them. So this is an integer, and this is a constant, which is now known as Planck's constant, which he got simply by fitting, okay? So he put a constant and he fitted to the experimentally known data, okay, for the black body radiation, and he found that constant there, okay? So you see, if you have a certain single frequency, obviously in a Noven you have many of them, but suppose you have a monochromatic electromagnetic radiation, like a single wave, okay? Then the energy, contrary to the classical intuition that, you make the intensity of the wave bigger in a continuous fashion, okay? And you can make the energy as big as you want. Remember, the energy is the square modulus of the wave, essentially. Okay, so you can make it continuously increasing or decreasing. Not so, Planck was saying. Okay, if you have a certain frequency, you can have just multiples of h. No, not an arbitrary number. So instead of having a continuous value of the energy, now you have so-called quantized value. Quantized in the sense of discrete. Okay? So that's probably the origin of the name. A quantum is a given amount, okay, which you cannot make a fraction of it. Okay, it's a unit in some sense. Okay? So this unit is h nu. So you can have 1 photon, 2, 3, okay? So this, by now you know, is the energy of a single photon of frequency nu. And you can have 1, 2, 3, 4 photons. An arbitrary number, but not 2.5 photons, okay? So this energy is impossible to have, okay? Obviously, you shouldn't be misled by what I say. I'm not saying if you have a thermodynamical thing, then there is an average number of particles, an average number of photons. This is a continuous number. So in this sense, it is reasonable to talk about, on average, having 3.4 average photons. But that is not meaning that there are 3.4 photons, okay? In the same sense as if you run a coin, you can have just head or tails. On average, you get, say, if you associate 0 to 1 and 1 to the other, on average, you get 1/2. It doesn't mean that you get 1/2. You get either one or the other, but on average, okay? So in the same, say, spirit, the average number of photons is something, but the actual number of photons is always discrete. Okay. Is this clear enough? Okay, so he was able to solve this paradox of classical physics with this very simple idea. And in fact, when we will do the harmonic oscillator, we will do a calculation that is essentially mimicking what Planck had in mind when he calculated this famous Planck distribution. Okay? So wait a little bit more and you will understand this, how it comes. Okay? It is essentially small calculation about harmonic oscillators. If you calculate the average energy of an harmonic oscillator, okay, in classical physics, you know that, for instance, the average potential energy is equal to how much it is? Do you remember in classical physics? The average kinetic energy of a particle in one dimension, for instance, at a temperature T. Yeah, in one dimension is just kBt over half, okay? If it is in 3 halves, okay? And the average potential energy of the harmonic oscillator is exactly the same, kBt over 2. Okay? So the average energy, which is the sum of these two, is just kBt, classically. Well, if you do the exercise quantum mechanically, okay, and we will learn how to treat p squared over 2m plus this object here, and this will be our first simple exercise. It's called the harmonic oscillator. We'll calculate it, and we will do exactly what Planck must have done, probably in his mind, to obtain deviations from this very simple thing. You will see how nu or omega enters into the game. Here you see there is no reference to the k over m square root is omega, is the frequency. You see it doesn't enter here. in quantum mechanics, it enters. Okay? And we will rediscover Planck's law. Okay. The second thing which somehow made people very suspicious about classical physics, how it worked, was was an experiment that is called photoelectric effect. The effect itself was discovered in 1887, I think, by Hertz. Okay? Essentially, the thing is like this. If you have a metal, okay, and you shine high energy radiation on it, okay, so what you know are essentially photons, or X-rays or gamma rays, then what you get is that particles, electrons, are emitted from the metal. That is exactly a type of experiment that people do now here routinely at the synchrotron. Okay? They are called photoemission experiments. They have a metal, they shine their X-rays that are produced by the synchrotron, X-rays, on the system. They go and measure the electrons coming out, and they can map their bands, their properties, and so on. Okay? So the photoemission experiments are just based on this very simple experiment that was devised long ago by Hertz. The experiment, however, had some puzzling features. First of all, if you have a light of a certain frequency, nu, what people knew experimentally is that no matter how intense is the light, if nu is too small, you get nothing. Okay? On the contrary, if you have here nu, and you get, for instance, the intensity of the light, you get 0 for a while. And after a certain nu, 0, you get electrons coming out. Then you can measure the kinetic energy of the electron, okay? The p squared over 2m, kinetic energy. And you plot it here, kinetic energy. If you measure the kinetic energy, obviously, well, up until here you have just 0. You have nothing, so. Then if you measure the kinetic energy as a function of nu, it's a nice straight line, okay? So the more increase nu, the more increases linearly the kinetic energy of the particles coming in. Obviously, they come in at different angles, okay? So you should have detectors all around, but if you measure the kinetic energy, it increases with nu, okay? So once again, the intensity of the what you see is obviously, so the current is obviously sensitive to the intensity of the field, okay? So if you increase the intensity, you shine more photons, you get more current. But the kinetic energy is not sensitive to the intensity of the fields. It's just due to the nu, okay? And in particular, if nu is too small, you get nothing, no matter how intense. So you can make a very, very intense electromagnetic radiation, but with a frequency that is too small, for instance, microwaves, nothing. The microwaves might cook a lot your dish, okay? But they're not able to kick electrons out of the metal. Okay. Well, Einstein was the first who understood that this idea was crucial to understand this experiment. He said, the photon, this particle, this electromagnetic radiation is really the quantized objects that Planck was having in mind. Okay, and he gave a name, he called photon. Okay, so this object hits an electron that is in the metal, essentially, well, it's not at rest, but it's a very small velocity, okay? Gives energy to it, hits the electron, And due to the large energy that this object has, how much? Well, h nu, as Planck was suggesting, gives this energy, and the electron acquires so much energy that it escapes from the metal. To escape from the metal, you need some energy, okay? Because, well, there is a minimum energy that you need, which is of the order, depends on the metal, it's of the order of a few electron volts, okay? So a metal is like a trap. The electrons stay inside, they are pretty nice and comfortable. If you do some work, you can take them out. But you have to provide certain energy. This is the energy that you have to provide. If you have too low energy to give to the electrons, they are not able to exit, okay? There is not enough. It is called the work function. Work function. It is the minimum energy you have to provide to an electron to just get it out from a metal, okay? So that explains why, if the frequency is too low, you do not have the minimum required to get it out. Obviously, after you have enough energy, you spend some energy to get it out, and the rest is kinetic energy that the electron has, okay? And obviously, the kinetic energy is simply h nu, the energy you provided, minus the work function that is the minimum to get it out, okay? So you see immediately that the kinetic energy is linearly proportional to the energy of the photon that was kicking the electron, okay? And there is a shift, which is this, okay? So this is just a straight line with some offset, okay? So you see that naturally explains the experiment. And the fact that this object here was really almost like a particle hitting the electron was finally confirmed by Compton in 1923. He did a series of very nice experiments that were basically the following. Shining X-rays or gamma rays, I forgot exactly what he was shining, on a material, so on the electrons on this material. And if you shine a certain, say, gamma ray, what you will see is that the gamma ray exits out, but generally speaking, with a different frequency, nu prime. And also, there is a certain electron that is hit by the photon and is emitted. And he discovered that this is essentially a billiard ball experiment, okay? So a particle, like a billiard ball, hitting another ball and being scattered by it and obviously kicking the ball, okay? And if you apply energy and momentum conservation exactly in the same way as you do when you do just very simple classical physics with the billiard balls, okay? So the energy is clear, okay? The energy of this would be p squared over 2m, for instance. The energy of this is just h nu and h nu prime. What about momentum? Well, the momentum of the classical particle is obvious, is p. But Compton realized that in order to make everything consistent with the simple rules of billiard physics, you have to assign a momentum also to the X-ray or to the gamma ray, and this momentum was just the energy h nu divided by c. Okay, so let me just do a little bit more of manipulation. So the momentum is the h nu divided by c, or if you remember this, you can write it as h over lambda. So h over the wavelength, or if you introduce a 2 pi, so you divide and multiply by 2 pi, this quantity here is so often used in quantum mechanics, so often appearing, that you give a name. It's called h bar. Okay, so it's h divided by 2 pi. And this quantity here will soon meet again. This 2 pi over lambda is called the wave vector of a wave, okay? It's called k, 2 pi over lambda. We'll soon discuss about it more, okay? So another way of writing the momentum of the photon is to say that is equal to h bar times the wave vector, so times 2 pi over lambda, okay? By the way, another way of writing the energy is to divide again by 2 pi and multiply by 2 pi. Now, h over 2 pi is h bar, and 2 pi nu is called omega. It's the angular frequency, okay? It's just nu multiplied by 2 pi. So the energy is h bar omega, and the momentum is h bar k. Now you see there is a very nice correspondence between the two things. If you use momentum and energy in this way, and you apply the rules of momentum conservation and energy conservation, you describe Compton's experiment in quite a detailed way. Obviously, you have to use relativistic equations, okay? So generally speaking, you have to allow for energy being not just p squared over 2m, but the square root of p squared c squared plus blah, 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 okay? So, but relativity was known, 1905, okay? So this is much later. All right, so this is essentially all I have to say about photons in our course. The rest of it is mostly about electrons. If you have questions until now, otherwise I proceed 20 more minutes towards our first exercise. So the story about electrons starts a few years after Planck. It starts essentially in the lab of Rutherford. Rutherford was a very brilliant experimentalist in Britain, and he discovered that atoms are not made of just a jelly of positive and negative charges, okay, as it was supposed before. Electrons were discovered. It was known that there were positive and negative charges in the atom, but people before Rutherford thought that these were just scrambled around, okay? And therefore, the atom was a neutral object with positive and negative charges. But then he did experiments hitting with bullets the atoms, and he discovered that no, the nucleus, the positive thing, must have been very, very, very concentrated in the middle, okay? And the negative part, on the contrary, was running around, okay? Essentially, he discovered that there was a very high probability of bouncing back, and this is only compatible with the nucleus to be very concentrated. But in his very same lab, there came a theoretician from Denmark, okay, and this theoretician was Bohr, okay, he was just fresh of PhD, in fact, and he started working on models for atoms, okay, understanding energy levels in the atoms. So after all, there were these electrons running around the nucleus. It looks like a planetary model, but obviously if you apply the rules of classical physics, a negative charge running around, like in the synchrotron, loses energy, and then it should just spiral on the nucleus and everything breaks. So he said, well, maybe there are some magic orbits that for some reason are stable, okay? So only some of them, however. A bit like this quantization idea. Not every orbit is allowed, only some special magic ones. And he was able, in fact, to write down rules. They are called quantization rules, to say exactly which orbits are good and which are not. And he studied a lot, hydrogen and the like, and it got results that were very nice with respect to experiment. Which experiment? Well, people knew, so this is the model. You have your nucleus and negative orbits due to the electrons. Some of them are stable and the others are essentially impossible. The energy is always related to the radius of the orbit, like in the planetary motion. The experiment known were the following. It is known that when atoms emit or absorb radiation, they change, they can emit or absorb radiation, okay? You look at the radiation coming from the stars, for instance, and for instance, you can see that if you examine the spectrum, there are some black lines, some missing frequencies. The reason why there are some black lines is that the light coming from the star at those special frequencies is absorbed by elements that are around the star, okay? So the star emits a broad range of things, but some frequencies are absorbed by what? By certain specific atoms. So somehow the black lines at particular frequencies, which were very well known and measured, are like the fingerprints of whatever is around, okay, which is absorbing that specific frequency. So it was known that there were very, very precise frequencies where atoms, for instance, hydrogen, interstellar hydrogen, absorbs frequencies and also emits, because there is also an emission spectrum that is exactly in the same position. So in some sense, there were lots of data regarding absorption and emission of atoms due to observations of light coming from the stars. And this data, pretty detailed, fitted exactly with Bohr simple atom calculations, okay? So he was able to invent rules for what are the possible orbits in such a way that the difference in energies between the orbits, okay, was exact. So if I call En the energy of orbit number n, then En minus Em, so n and m, two orbits, for instance, nearby or not necessarily nearby, well, these precise energies that we was able to calculate, their difference was h bar, a certain frequency, which was the frequency of the line seen to be missing or seen in emission in the experiments, okay? So in some sense, this was a very nice relationship between what electrons do in the atom and what you see regarding the light emitted by the atom or absorbed, okay? So this is Planck and this is Bohr, okay? They are related in some sense, okay? What the atom absorbs or emits is quanta of frequencies that are measurable. And after that, well, there was a lot of activity in this. Sommerfeld, Bohr calculated a lot properties of quantized orbits, still in this very ad hoc fashion, okay? Schrödinger was not there to provide them with a theory, an actual theory. They had very ingenious rules for quantizing the orbits, and still before Schrödinger, another guy had the idea. The name of the person is De Broglie, was a French physicist. He understood that perhaps these magic orbits of Bohr, they were such that if, so I say this orbit here, it has a certain momentum, p. Well, if you associate to it a wavelength, you might say, how do we associate a wavelength? Well, look at that. In the physics of photons, people knew that the wavelength should be also a momentum, Compton, okay? So on the contrary, if you have a certain momentum, you can think of it as a wavelength, okay? So this is just h over lambda. And he realized that if you try to fit this wavelength lambda in the magic orbits, well, the magic orbits are such that, well, I didn't draw it nicely, but are such that they fit an integer number of wavelengths, okay? All the other orbits would not fit an integer number, okay? So he said, maybe there is a wave nature, really, of these things, okay? Was a suggestion more than a theory, okay? So it's realizing that you can reread the magic orbits of Bohr as the ones for which an exact number of a certain wavelength associated to the momentum of the electron really fits the orbit. Unfortunately, he was too slow in really making this thing an actual mathematical theory, because Schrödinger quite soon published his famous paper in which he actually wrote the first mathematical equation to calculate all this, okay, in a rigorous way, in some sense, in a well-established fashion, okay? So this is what we will come to next, okay? So, well, just before I finish this kind of introduction, let me just point to you that the wave nature that de Broglie was having in mind is by now well established. For instance, the experiment I showed to you about IBM, the chorale, the waves that you see are just the waves that the electrons are in their deep nature, okay? Yes. And so by now the wave nature is absolutely seen in many, many experiments. In particular, one place where people started looking for the wave nature is obviously making gratings. You know that if you make a wave impinge on a series of pillars, you get curious interference phenomena, okay? So they started looking for the wave nature due to gratings, and in fact, already in early experiments, they saw that really there are interference phenomena due to electrons wave, pretty much like the Bragg reflections, okay? So there are specific angles at which you get constructive interference, and therefore the beams are reflected and all the other angles are not good, okay? So interference experiments are, since the 30s, kind of given hint to the wave nature of the electrons, but by now are absolutely well-established facts, okay? So if you have questions, this is, I realize, just an introduction, so I urge you to read the first chapter of any book in quantum mechanics. Essentially, any book has a discussion of black body, Compton, photoelectric effect, Bohr, and de Broglie, and all these things, okay? If you do not have questions, I would at least set up what will be our first exercise in quantum mechanics. I will not, obviously, prove for you Schrödinger equation, okay? Not even Schrödinger proved it, okay? He wrote it very ingeniously, and I'm much more less gifted than Schrödinger, and therefore I will simply write it for you. But in order to make it more reasonable to your understanding, I will start with something that is really wave physics more than quantum mechanics. By the way, some of the phenomena of quantum mechanics are really wave physics, okay? So they are also encountered in classical physics when you have waves. There are other aspects of quantum mechanics, okay, like, well, we'll discuss, which cannot be just explained in classical terms, okay? But some aspects are just classical wave physics. So the idea is the following. I want to describe a particle, okay, so something that is really an object that hits a screen, for instance, in a way that has a wave nature. Well, you know the waves, for instance, the simplest wave is a monochromatic plane waves, like that. Okay? So if I plot this as x, if I plot, for instance, the amplitude of the wave, this might be, for instance, cosine of, let's see, 2 pi over lambda x. Okay? Lambda is this distance. You realize that if you change x into x plus lambda, so any point here, for instance, you sum lambda, this makes simply a 2 pi contribution, and therefore this is indeed the wavelength. Okay? So this is a way of writing a wave, a pure wave of a wavelength lambda. Now, this is the reason why it is very nice to call this parameter in front k, okay, as we did before. So this object, I will write it as cosine kx. The wave vector is 2 pi over the wavelength. All right. Now, an object like this lives forever, okay? So it is, for instance, close to 1 here, but it's close to 1 wherever you want, at the infinite distance. This cannot be a point-like particle, right? What could be a particle is something that it is very large at a certain point, then soon becomes smaller, okay? If you look at some wave like this, okay, so a wave that is large in the point, but then oscillates and becomes very small, then you might, from a distance, don't see the small winkles there and say, hey, this is a particle there, okay? Depending on the sensitivity of your apparatus, it looks like a point, right? Now, this object is called a wave packet, okay? It's a wave, but it's so well localized that can be exchanged for a particle in certain experiments, okay? This is what we want to learn to describe, because that's our most likely explanation for the dual nature of quantum particles. They are particles, but they behave like wave. And obviously, when they are localized, they must be probably wave packets. Okay, so how can you make a wave packet starting from there? Well, the procedure is you have to make sum of several waves in order to have interference of those waves such that they interfere constructively at a certain point and they interfere destructively everywhere else, okay? So by summing several waves with several k's, maybe I can get from here to there, okay? That is the process that I want to describe for you next. And in fact, the process itself, it is essentially Fourier transform. So let me define psi of x to be just, well, rather than working with cosine of k of x, I will work with e to the I kx. The exponential with the complex exponential with an I, which you know it's cosine of kx plus I sine of kx. This is much more useful in many analytical steps, okay? So I will use, rather than the cosine or the sine, the complex exponential. So suppose that you sum several, okay? Several of those e to the I kx with some factor g of k. In fact, they are so several that I really assume that I have an infinitely many of them, and I have an integral. Let us work in one dimension, by the way. Okay, so both x and k are one-dimensional variables. Okay, So I superimpose an infinite amount of plane waves with different momenta, okay, weighted by some weight function, which is g of k. And in order to normalize things later on in an easier way, let me put the square root of 2 pi there. Okay? So this is an integral from minus infinity to plus infinity. And those of you who have studied Fourier transform, they know that this is psi of x is the Fourier transform of g of k. Okay? But the way I want you to look at this mathematical relationship is that I am superimposing many plane waves, okay, with a certain weight, g of k, okay, in order to create possibly some wave packet. That is what I want to do. Okay, is this clear? This is the goal. For instance, let us be more concrete. Let us take as a weight function, g of k, the following thing. So this is k, and this is g of k. I will take a certain k0 value, and then I will take a Gaussian centered around k0. Okay? So this is just a plot. This is a Gaussian. So g of k, for me, is some constant, c, times e to the minus alpha k minus k0 square. Okay? So it's a Gaussian centered at a certain position, k0. Alpha will tell me how broad is this weight function, how broad is this Gaussian. And this is a normalization constant, okay? Which I will tell you next time how it should be chosen, okay? It doesn't really matter because this is just a constant, okay? If you change it, it changes psi by an overall constant. So it's not very important. This, on the contrary, just tells you how large this thing is. The larger is alpha, the more narrow is this thing. So it's inversely proportional to the width of the Gaussian. Okay? So next time we will carry out an exact calculation, exact analytical calculation of this wave packet with this Gaussian weight. Okay? And the basic integrals that we will have to use is essentially an integral that you probably know very well. You know that if you have the integral of, in dk, square root of 2 pi e to the minus k square over 2, this is equal to 1. Okay? You've probably seen this many times. Okay? The integral of a Gaussian appropriately normalized with a factor 2 there is 1. Or if you want, is 2 pi, is square root of 2 pi if you don't put the square root of 2 pi there. Well, obviously, with this, you can do more. You can put, for instance, here some a, and if you rescale the a here, you realize that this is square root of a. Okay? This is very, very simple to show. And with this, you can go and become more and more brave in your integral calculation. You can put the factor k times some arbitrary constant there. Okay? So rather than just a Gaussian with k squared, you now have a linear term also. Well, you know that when you have a quadratic and linear, you can recombine into a quadratic form by shifting. Okay? So by a very simple shift of k, which you can reabsorb in the integral, you can prove for me that this is just equal to e to the j square over 2a. We'll do it next time, don't worry. It's just to anticipate what is the basic analytics that you need to do to calculate what I'm proposing to you. Okay? So this is the basic integral we will have next time. And even more, j does need to be a real constant. In fact, let us use ix there. Then this becomes ix square, okay? And I square is just a minus, so this is minus x squared. So you see that the e to the ikx integral over k with a Gaussian is just a Gaussian. Okay? So this is what next time we'll use to calculate in detail the wave packet that I'm proposing to you. Okay? And from that, I will try to continue my discussion. Okay? So if you have no more questions, I would stop here. Yes?
We know from Bohr model that electron turn around proton on some orbit.
Yeah.
And how can this model interpret the electronic capture?
The electronic?
Capture. We know that electrons can be captured by the proton.
Okay. So the question is, the Bohr models, okay, has a prescription to calculate orbits of electrons, and he was wondering how can this explain the electronic capture, I mean, due to if you electrons can be both emitted from an atom, but they can also be captured sometimes, okay, to form negative ions, okay? How can this explain? Well, obviously, depending on the case, you have to do calculation, but the important thing is that there are energy levels, okay, in the atoms, okay, that allow for an extra orbit with an extra electrons to be stable, okay, with respect to the two things being at plus infinity. So you gain some energy. So with respect to having the atom here and the extra electron far away, there is some energy gain if you put the electron inside. That depends on the system. It's not guaranteed. Certain atoms like to have an extra electron. Certain atoms do not like. Okay? Atoms like fluorine, chlorine, which have an almost full shell, they just need a little bit to fill the shell. The chlorine, for instance, they love electrons. Okay? So they capture things just to make the shell complete. Okay? Obviously, you have to calculate the energy levels. I remind you, it's a very complicated calculation because you do not have a single electron. You have several of them. They interact, and they obey quantum mechanics. Okay? So the calculation is terrific. It's very, very complicated quantum mechanical many-body problem that you have to do. But in principle, if you do the calculation, you would realize that the energy that your compound system, atom plus electron coming in, is better than having them separately. So Bohr model, I don't know how long it can go in explaining things. I mean, Bohr model is just a model that was, invented, but then, Schrödinger equation is much more powerful than Bohr model. So I do not know the exact answer to your problem because I am not so fond of the Bohr model to know exactly if it describes the capture of the electron. I have no idea, really. But what I can tell you that the deep physics behind Schrödinger is that depending on the number of electrons and on the number of shells that are almost to be filled, there are cases where the electrons might be captured because they make the shell full. Okay? On the contrary, there are cases where the electrons are very tightly bound. For instance, there's only one electron in the shell, and these electrons are very nicely given around. Certain atoms tend to give them their electrons around and become positively charged. So this explains why ions emerge. So atoms that get charged positively or negative by just donating or receiving electrons. They're a stable quantum mechanical object with one more or one less electrons, or two more or two less, depending. Okay? In principle, you should be able to calculate that with Schrödinger equation, but it's a complicated thing. Okay? So I don't know if it answered your Your questions?
In this case, can we talk about quantization?
I did not understand the question.
In case of capture, electronic capture, can we talk about quantization?
The question is, in the case of electron capture, can we talk about transitions? Well, you are changing the system from having n electrons to having n plus 1 electrons. All the energy levels rearrange accordingly, okay? So you should be careful. When you have the same number of electrons and you just excite an electron by absorbing a photon, the number of electrons doesn't change. But here you are changing the number of electrons. Electrons interact, and therefore the levels that they form change when their number changes. So this is an extra piece of complication. So I encourage you not to think much about capture of electrons unless you really do it for a business, okay? It's a very complicated thing. So it's not the kind of thing that you would like to understand at the first lecture in quantum mechanics. In fact, you will not understand even on the last lecture in quantum mechanics, okay? Because it's a many-body problem, and we'll do just one-body physics. Many-body is still a frontier in many aspects, because dealing with the interaction of the electrons and their quantum nature makes the problem very, very complicated, okay? So this.
I wonder if we can have a support like this for us.
If you can?
Yes, if I can have this note.
The notes? Yes, I'm going to give them to Patrizia and Sandra to distribute them to you, but I will also give to you the PDF directly so that if you have a computer, you can look at it on the computer together with having the paper version, okay? So you will have it, okay? But I remind you, it's not a book, it's sketchy notes. So it reminds you of what we have said, but sometimes I say, as seen in class, means that there is some algebra. I don't put the algebra, but you should be able to fill the gaps, okay? So I will send them to you. So if there are no more questions, I would stop the lecture here for today and see you tomorrow, okay? Bye-bye.